Okay, introduction to analysis of variance. Just going to go through some background work on the analysis of variance. We have Carl Pearson, William Gossett, and Ronald Fisher, three stars of the statistics that that are taught in this course. Okay, so we're going to do an introduction to analysis of variance today. We're going to go through some of the core calculations to create what's referred to as the source table. Over the next couple of weeks, we'll also do the comparisons amongst means, which is the next step. So to get things started, I'll introduce the problem that we're going to complete analysis on. So once again, it's analysis of variance, or ANOVA, or ANOVA. Okay, so my new study for the analysis of variance is I survey 3 groups who voted in the last federal election. I had the respondents complete a survey that contained 10 Likert items probing perceptions of government. So the items range from 1 strongly disagree to 4 strongly agree. The responses to the 10 items were summed to give a total score, right? So the score would be 10. Maximum score is 40. Minimum score is 10. But I have 3 groups I administered my scale to. I have university undergraduate students, university graduate students, and college students. So this is a new inferential test, a univariate test. Everything we've done before has been either 1 mean, 2 means. Now we are extending our work to 3 means. Okay, so what I do is I sample 9 people from each of the 3 groups. I randomly sample from the population. I have 9 undergraduates, 9 graduates, and 9 college students. Fairly straightforward. This is my data. For the 9 college students, their perceptions of government, the mean was 25. For the university graduate students, the mean was 30. And then for the university undergraduate, the mean was 20. Okay, so I got 3 groups. Okay, the first thing to address is, and this would be one of the first questions, why wouldn't I just run all pairwise comparisons as a t-test, right? So really what I could do if I wanted to, I could run a t-test, an independent means t-test to compare the college to the undergrad or grad. I could compare the college to the university undergrad, and then I could compare the university grad to the university undergrad. So I could do 3 t-tests. First t-test would compare college and university graduate. The second t-test would compare college to university undergraduate. And the third t-test would be university graduate to university undergraduate. Okay. And these would be 3 t-tests. Now, what we have to look at is, and what's critical, if I do my 3 comparisons, right? So I call them t-tests, but they're 3 comparisons, so 3 t-tests. So the first t-test would be compare the undergrads to the grads. The second t-test could be compare the undergrads to the college. And the third t-test would be compare the grads to the college, right? 3 separate independent t-tests. So I'm running 3 inferential tests, 3 independent means t-tests. Now, assume that the null hypothesis is true for each comparison. So the null hypothesis is true. There is no difference between the undergrads and grads. There is no difference between the undergrads and the college. And there is no difference between the grads and the college. Okay. Our little probability tree. So if I run my first t-test, the correct decision is to fail to reject HO, right? Because the null hypothesis is true. What I would want to do is fail to reject HO. Now, if the null hypothesis is true, I set my cutoff where we would get our t-critical. And our t-critical would be for, my alpha would be 5.05, right? So 5%. So for the first t-test, the correct decision, which is here, is to fail to reject HO. And if my alpha is 0.05, that would happen, the correct thing would happen 95% of the time, right? So that's my first t-test. My second t-test assuming I failed to reject on the first one, my second t-test is the undergrad to the college. Now, I should not reject HO, but if the null hypothesis is true, if I ran a study 100 times, 5 times out of 100, I would reject HO, which is the incorrect thing to do. And that's just through random sampling. So for the second t-test, the correct decision, once again, is to fail to reject HO. My third t-test, once again, the correct path is fail to reject HO. So if I look at my table here, I've got 3 pairwise comparisons, and I can do my little probability tree for each of them. There's only one path that is correct, and that path is here. Fail to reject HO, fail to reject HO, fail to reject HO. Now, that one path is the only correct path. And I can figure out that, and everything else is wrong, right? So if I figure out this probability here, 1 minus alpha, for the number of comparisons I'm doing. So if I take 1 minus alpha and times it by 1 minus alpha times 1 minus alpha, which is really 1 minus alpha to the power of 3, or cubed. So 0.95 times by 0.95. That's the probability of doing the right thing for all 3 comparisons. Everything else is a mistake, right? In every other situation in here, I have rejected HO at least once. So the path at the bottom here, I reject HO 3 times, which is bad. The next path up, I reject HO twice, which is bad. Next path up, reject HO twice, bad. And then the next path up, I reject HO once and do the correct thing twice. So the only true correct path is the top one. Okay. But in terms of my error rate, I want to figure out what is the probability of my rejecting the null hypothesis at least once. Okay. So I have 3 comparisons. So let's see here. So here's my correct path. Right, so I can, let's fill her in with the yellow. So the correct path occurs 3 times. That's 1 minus alpha. So my family-wise error rate is everything else. So I take my 1 minus alpha times by 1 minus alpha times by 1 minus alpha, and then subtract that from 1 to tell me what is the probability of rejecting the null hypothesis at least once when I shouldn't, because the null hypothesis is true for in all cases, for all comparisons. And as we see, that formula is right here. So my family-wise error rate is, okay, that's okay. So, or N, or see, that's N. Well, yeah, I'll call it N, but it's really, I'll call it okay. So my family-wise error rate, if I look at this as one study, right? So one study, one analysis, one statistical analysis overall. Am I running 3 independent t-tests? My family-wise error rate is not 0.05, it's actually 0.1426. So if I were to run this study, I would find that I would reject the null hypothesis at least once, 14% of the time. So out of 100 studies, even though the null hypothesis is true, there's no differences amongst the 3 groups, I would reject the null hypothesis 14 times out of 100. Okay, that's not too bad for 3, but now if I up this to say 5, now it's up to 22%. So if I do 5 t-tests, almost 1 in 4 will lead to a rejection of the null hypothesis. If I do 6, I'm up to 26%. If I do 7 t-tests, there's a 30% chance that I'll at least reject the null hypothesis once. So, and this is referred to as the family-wise error rate, right? So it's not the error rate for each individual comparison. It's the error rate when I think of all three comparisons as being part of a family. So I don't look at it as the one t-test. I look at it overall. What is the overall error rate for the family of three t-tests? And in this case, for our case here with three, the error rate is 14%, right? It's not, my error rate's not 0.05, because I have to look at it not from the individual t-tests, but all three t-tests, which form my study, my analysis. And all three t-tests is really then the likelihood of me rejecting the null at least once in my one, and for my study and my one kind of like analysis in terms I want to do, if I want to look at it from the perspective of the all three comparisons. So that's referred to as the family-wise error rate. So what I need is, I need a solution that allows me to complete my analysis but have a proper adjustment for my my alpha. I want my alpha to still be 0.05, and I don't want to run three independent t-tests. Okay. So what do? We do the analysis of variance. Okay. The analysis of variance is analysis of variance. And we'll explain in a sec conceptually what that means. So I'm kind of looking at the means, but I'm looking at the variances of the groups within my study. And it's referred to the one-way analysis of variance with one independent variable. So it's a univariate test. In this case, it's the student's score on the election scale, politics scale. My null hypothesis, mu1 equal to mu2 equal to mu3, right? There's no difference amongst the three means, college, grad, undergrad. The alternate hypothesis is at least one population mean is different from another. Now, sometimes you'll even see it in textbooks where they'll say the alternate hypothesis is mu1 not equal to mu2 not equal to mu3. That's technically incorrect. That is one possible outcome where the null hypothesis is not true, but another option could be mu1 not equal to mu2, and mu2 equal to mu3, right? So you do have that possibility. So there's multiple possibilities when it comes to the alternate hypothesis. So if you see the alternate hypothesis, mu1 not equal to mu2 not equal to mu3, it is incorrect. Okay. The analysis of variance is exactly what it says it is. It's partitioning of variance. And when I look at my study, my college students, the mean was 25. The mean for the undergraduate students was 20, and the mean for the graduate students was 30. So I have two sources of variability here. There's the amount of variance that occurs within each of the respective groups. So in the undergraduate group, not every student had the same score. So there was variability within that group. For the college students, there's variability within the 9 college students. Not every college student had the same score. Finally, for the graduate students, the mean was 30, but not every person had a score of 30 on the scale. That's referred to as my within groups variability. In analysis of variance, there's another source of variance, and that's the variance that's caused by the difference between the group means. So not only are there differences in terms of there's dispersion within each of my groups, my 3 groups are separate from each other. Okay, so each group, they're not all over top of each other. They would be for the null hypothesis, but if the alternate hypothesis is true, the groups will be in different ways, can be separated, distinctly separate from each other. And what the analysis of variance does is it looks to see, is the variance of my study, is the variance that's due to the difference between the 3 groups and how far apart the 3 groups is that variance larger than really essentially the variance that's within each of the groups? If the variance that's caused by the groups being distinct and separate from each other is greater than the variance that's within each of those groups, then I have evidence to suggest that there are differences amongst the means. Now, my conclusion is not that the what are the specific differences amongst the means, my conclusion is, when I reject the null hypothesis for analysis of variance, is that in terms of the overall variance in the study, in my analysis, more of the variance is caused by the difference between the groups than the variance within the groups. And that's analysis of variance. Okay. So, in terms of the null hypothesis, if I look at individuals from the population, there's the mean for the population, right? So there is an overall mean for the population. And because it's distributed and will be normally distributed, we refer to people who like the spread of the scores as error, right? Those are individual differences, and they're caused by just people's just general makeup, right, and experiences. So there's like the overall population has a mean, and there's a spread of scores for the population, that center around the mean. So for the null hypothesis, in terms of the spread, the variability in the scores is based upon the mean and the amount of dispersion that occurs around that mean, in terms of like there's just variability in the general population, and that's referred to the error term. If H1 is true, then an individual's score on the scale is based upon the overall grand mean for the population, plus individual differences, which is the error term, plus the influence of group membership. So for the analysis of variance, the spread of scores from the overall grand mean for the whole population, the spread of scores is dependent upon two factors. One factor is just the general dispersion that's caused, we call error, that's just due to people's individual experiences in general. But then there is the specific targeted influence of group membership. And that will be whether they're college, undergrad, or grad students. So if I'm looking at analysis of variance, here is the overall variability for the study, right, which will be all the individuals, I through J. I is the 1 through 9 of the individuals. J is the group membership. There's 3 groups. The overall variability or dispersion in my sample of 27 people or students is going to be made up of how far each person differs from the grand mean, which is driven by the influence of group membership, the experience of being a college, undergrad, or grad student, plus the error term. So what I'm doing in analysis of variance is I'm partitioning out. I have the overall grand mean for the population, and I have the overall grand mean for my sample. I'm going to partition out what I see as the influence of group membership and the influence of just general error, right? Just the individuals within the groups differ. And what I'm hoping is the contribution of group membership far outweighs the contribution of just the general error in our measurement. And that's what analysis of variance is. So I'm partitioning variance. The overall variability of the 27 individuals in the study is made up of how much they differ from the mean overall, and the amount that they differ is driven by their group membership as an influence upon their score and the general error in my measurement. I'm not measuring everything about them. So for the next part, what we'll do is we're going to walk through the calculations that we do to partial out the influence of group membership in terms of its contribution to variability and the error term.